Hello, everyone, and welcome back to our series on knowledge tracing. Today, we're focusing on a critical aspect of learning that many models overlook: time. We'll explore TISAKT and HawkesKT, two models that don't just ask what a student did, but also when they did it. These models treat learning as a dynamic sequence of events, making them incredibly powerful for understanding and predicting student behavior. Let's dive in. Here's our plan for today. We'll start by addressing a very important question. If we've used time in models before, what makes these new models different? We'll compare 4 different approaches to modeling time. Then we'll break down the core concepts of TISAKT and HawkesKT. We'll do concrete calculation demos for both models. After that, we'll discuss the key parameters and how they're learned. Finally, we'll explore how these powerful models can be integrated into your own research. This is a fantastic question. Yes, we have used time before, but TISAKT and HawkesKT represent a fundamental shift in how we use it. Earlier models treated time as a simple passive forgetting factor, a battery that drains or a page that fades. The time parameter was fixed and applied uniformly. TISAKT and HawkesKT are different. They treat time as an active, first-class feature. They model learning as a sequence of events where the timing of each event directly influences future behavior. This is a much more sophisticated and realistic approach to understanding how humans learn and forget. Let's break down the core concepts. TISAKT enhances the attention mechanism by embedding time intervals into vectors and using them to compute attention weights and control state updates. It's a way to make attention time-aware. HawkesKT takes a different approach, using a mathematical framework called a point process. It models the intensity of learning at any given moment, which is influenced by a baseline level of motivation and the decaying influence of past events. Crucially, it can model cross-excitation, where learning one skill makes learning another more likely. Let's walk through a TISAKT example. We have 3 past questions, varying in similarity and recency. First, we calculate a time embedding for each, which is a value that decays over time. We then combine this time embedding with the content similarity to get a combined score. Using softmax, these scores become weights. Notice that the most recent and similar question, Q3, gets a dominant weight of 0.67. However, the recent but dissimilar question, Q3, also gets a significant weight, showing that the model is considering the temporal proximity even when the content doesn't match perfectly. Now let's look at a HawkesKT example. We want to calculate the learning intensity on day 5, given a history of correct and incorrect answers. The formula sums the baseline intensity and the decaying influence of each past event. Correct answers have a positive influence, incorrect ones negative. We calculate the contribution of each event. The most recent correct answer has the largest impact, while the older events have much smaller contributions. The total intensity of 0.285 represents the model's estimate of how active the student's learning process is at this moment. This is a powerful way to model the dynamic ebb and flow of knowledge. The power of these models comes from their ability to learn complex parameters from data. In TISAKT, the model learns how to best represent time and how to balance the importance of content versus recency. In HawkesKT, the model learns the baseline motivation of the student, the impact of different types of events, correct, incorrect, how quickly their influence decays, and even the transfer effects between different skills. This data-driven approach makes the models highly adaptive and capable of capturing the unique learning patterns of individual students. Let's re-emphasize the fundamental difference. Traditional models use time as a simple, passive discount factor, a battery that drains. TISAKT and HawkesKT use time as an active trigger for events. The decay rules are not fixed, but learned from data and can vary for different types of events. These new models can distinguish between different actions, like reviewing versus skipping, and model how learning one skill can influence another. The parameters are dynamic and can be personalized to students and skills. This is a shift from a simple forgetting model to a sophisticated model of human learning dynamics. These time-aware models are a perfect fit for your research. You can integrate your cognitive data like eye tracking directly into the event modeling. For example, assigning a weaker influence to events that occurred during skimming. The dynamic forgetting parameters can be tied to fatigue levels, making the model even more realistic. Most excitingly, these models can predict the optimal time for review, which is a direct input for your OCZ framework. You could use the learning intensity lambda T to decide not just what to review, but when to review it for maximum effect. Let's summarize. TISAKT and HawkesKT represent a major shift in knowledge tracing. They move beyond simple forgetting models to treat time as a fundamental, active component of learning. TISAKT enhances attention with time awareness, while HawkesKT uses a powerful mathematical framework to model the intensity of learning events. Both models view learning as a dynamic process, not just a static sequence of answers. This leads to more accurate predictions and a much deeper understanding of how students learn and forget over time. That's all for today's deep dive into TISAKT and HawkesKT. We've covered their core ideas, calculations, and how they represent a significant advance over previous methods. Now, I'd be happy to answer any questions you might have. Thank you for your attention. Thank you for watching. If you found this video helpful, please like and subscribe for more content on educational data mining and knowledge tracing. See you next time.